Hello everyone. Let's continue on the question number 36. We have here, which of the following statements is false? Is false about the kinetic theory of molecules. Objects are made up of a large number of molecules. Molecules are in constant random motion. There are both gravitational and repulsive forces between molecules. All molecules move at the same rate. Okay, let's start with the A. Objects are made up of a large number of molecules. This is actually true because if we consider a certain mass of an object, microscopically it's made of a very large number of particles or molecules or even atoms. Okay, so it's not just like one single bulb, it's not like one single part, but it's made of a very big number of particles that we cannot see with our eyes. Okay, so for A it's correct, it's not false. For B, molecules are in constant random motion. That's true as well. Let's consider a certain liquid. The particles that we cannot see again are actually moving all the time. We're going to see that in another question in this video, how we can prove that the particles are moving all the time and they are not just like fixed in one place. Okay, so the molecules are moving all the time. So for the C, there are both gravitational and repulsive forces between molecules. All of those are representing the case of the what we call kinetic theory of molecules, or theory of kinetic molecular theory. So there are both gravitational and repulsive forces between molecules. Molecules are charged, so if they have for sure same charges, there would be a certain repulsive electrostatic forces. They are repelling each other, so they wouldn't be occupying the same space. They are attracting each other because of their masses, but the gravitational is very tiny in front of the electrostatic one. So this one is very weak in front of this one, but it exists actually. All molecules move at the same rate. This is the incorrect proposition here, because let's think that is a very busy highway here where cars are moving each in a certain direction. So each car has its own speed, okay, but not all of them have the same speed. Some of them are just like moving very quickly at a higher speed. Some are moving slower than the others. It's the same here for particles. They are moving in a random motion or random movement, but it's not the same at not the same rate. Okay, they have all the same average, we can say average rate, but not each singular motion is exactly the same as for the others. Let's have a look at 37. An ideal gas of a given mass is compressed at a constant temperature. What happens in this case? The gas does work on the outside and the internal energy increases. the work or work done by the external environment on the gas, the internal energy remains unchanged. The gas does work on the outside and the internal energy decreases, or work done by the or on the gas by the outside and the internal energy increases. So to answer this question, we just need to remind this formula. This is what we call the first law of thermodynamics. It says that the internal energy as a change, the change of internal energy of a certain system, it's just like depends on the temperature or the absolute temperature only. That means the change of the internal energy will occur if the temperature changes. So here we have the process is done at a constant temperature. That means the temperature didn't change. Okay, so the delta U would be equal to 0 in this case. That means the U initial would be equal to U final. The internal energy is the same as in the initial and the final state. So where do we have here the energy stays the same? So here for the let's see, for the proposition B, work done by the external environment on the gas, the internal energy remains unchanged. Okay, here for the A it's not the 1, for C it's not the 1, for D it's not the 1, because energy here changes, here increases, and here decreases. Okay, so because of that we have that. 38. In the expression of the first law of thermodynamics, delta U equals Q plus W, which of the following correctly defines the sign of work? So let's pay attention please. Here we have here a plus. Sometimes you're gonna get delta U equals Q minus W. Pay attention to the sign in front of the W here. For our case here, in the question we have a plus W, plus the work. When it's the plus, that means it's the work done by the system, I mean. Okay, so the gas does work on the outside. W is negative. When we have the system containing certain gas, for instance, this is a cylinder with a piston. If the gas is expanding, that means it's pushing the piston to upward. So what happens here, it's losing the work, it's losing the energy as work. That means the W must be negative, so the A is the correct one. The gas does work on the outside. That means it's the gas doing this work. W must be would be positive. This is not actually logically possible. That must be a negative quantity. Okay, so the system is considering that it is losing the energy. Work done by the external force on the gas, W is negative. Actually it's not. If this state here positive, that would be correct, because now the work is done on the system. So if the work is done on the system, that means it's receiving the work. It must be positive, not negative. So for B and C, they are not correct. Always positive, those are not correct. Automatically the D is not correct. 39. Which of the following statements is true about Brownian motion? Before answering the question, let's have a look a little bit about at the Brownian motion. What is the Brownian motion? It says that if we have a certain fluid, it could be a liquid or a gas. The liquid and gases are made up of a very, very small particle that we call molecules. Molecules, we cannot see them directly with our eyes, neither with a microscope. Okay, so what do? We plug in a certain pollen, for instance, or smoke for a gas, particles that could be seen under the microscope. What we will observe is those particles are making some zigzag motions. This proves they are bombarded on all sides. What is responsible for this bombarding? The responsible for that is the particles making the substance, okay, or the object. This fluid is composed of particles. Those particles are just like hitting those smoke parts or pollen parts. So those observed they are moving in a random chaotic motion. This is what we call Brownian motion. So for A here we have Brownian motion is the random motion of liquid molecules. It's not exactly that. The Brownian motion shows us the motion of the particle that we plugged in, not the particles of construction of this liquid. Okay, Brownian motion reflects the random motion of solid molecules. For solid, a block of a certain matter which is solid as a state, the particles forming these blocks or solids are actually animated with a certain vibrating motion around a certain equilibrium position, so they are not freely moving just like in a certain fluid. Okay, so for solids we cannot see the Brownian motion. Here we have A and B are not correct. The intensity of Brownian motion is independent of temperature. This is not correct as well, because as we add heat to the certain fluid, water for example, the molecules will be animated with a certain higher kinetic energy. That means they will move faster. If they will move faster, they will hit the particles of the pollen or the smoke harder, so the Brownian motion would be more intense. Okay, Brownian motion is the motion of small solid particles suspended in the liquid. This is exactly the definition of that. For 40 here we have for an ideal gas of a given mass, which of the following process is impossible? Some of or one of these four is impossible to happen. As we are talking about an ideal gas, we can just like work with the ideal gas formula. PV equals nRT. Let's consider the quantity is not changing. The nR is constant. That means the PV over T is a constant. Okay, for the A, what do we have in A? We have the temperature rise, the pressure decreases, and the volume decreases. Okay, this is actually possible. For B, we have the temperature remains constant, the pressure increases and the volume decreases. Pressure for C remains constant, temperature increases, volume decreases. For D, we have the volume remains constant, the temperature increases, and the pressure increases. Here we have for A, the temperature rises, the pressure decreases, and the volume increases. Let's have a look at the equation. We have PV equals a certain constant times the T. Okay, so if V is significantly more than T rises, P must let's say a certain K times T. If the temperature rises and the pressure decreases, so volume must increase, just like to keep the equation balanced. Okay, if the V or the P is significantly decreases, the temperature is rising with a certain rate, so the volume at this case must be rising, so to keep the equation balanced. So for A it is possible. For B, we have the temperature remains constant, the pressure increases, and the volume decreases. We see here the temperature remains the same, so if T equals a constant, that means the PV is a certain constant K. Okay, the T now is among these K because it's constant. So here, if the where is the B? Okay, the pressure increasing, to keep that constant, the V must decrease, because here in this case it's the P is inversely proportional to V. With T we say it's a constant, which means the B is possible as well. Okay, let's move to the D before the C. The volume remains constant, the temperature increases, and the pressure increases. In this case we have the V is the one which is constant. Okay, so P would be KT. Okay, V is constant. As the temperature increasing, what must be happening for the P to keep the equation balanced again? In this form we see that the P is proportional to T in case of V is constant. If we increase the temperature, the pressure of this of that system will increase as well, so the D is possible. The remaining one, C, is the impossible one. Pressure remains constant, temperature increases, volume decreases. If P is the one which is constant, that means the V must be equal a certain K times T, so the V is proportional to T. If we increase the temperature, the volume of the gas or of the system must increase as well. So for here, pressure remains the constant, temperature increases, but the volume decreases. This is not possible actually. Okay, so this is it for this video number 8. Wait for the next video where we're going to start with the number 41. That's gonna be when a beam of light enters water from air, it undergoes the wavelength increases, the wavelength remains unchanged, shorter wavelength, same frequency, the wavelength remains unchanged, and the frequency increases. We're going to see what's gonna be the correct one in the next video. Until then, see you soon.